Hello and welcome to In Control, the first podcast on control theory. Here we discuss the science of feedback, decision-making, artificial intelligence, and much more. I'm your host, Alberto Vadon, live from a recording studio in Vancouver. Quick thanks to our sponsors, the National Centre of Competence in Research on Dependable ubiquitous automation. Our guest today is Cosimo Della Santina, Associate Professor in Robotics at TU Delft and guest researcher at DLR, the German Aerospace Center. He's the founder of the Physical Intelligence Lab and co-founder of Embodied AI. Welcome to the show, Cosimo.
Thanks, Alberto. Thanks for the introduction.
So, Cosimo, I'm extremely excited to have you today on the show. You're possibly one of the younger, if not the youngest guest that we had as a guest of the show. But despite that, you've already achieved a lot. You've somehow become a symbol of the emerging field of soft robotics. And so I'm really looking forward to delve into this topic together.
Thanks. You are too kind, and I'm also very much looking forward to the discussion.
So I generally tend to ask this question because I think there might be some links, let's say, between the career, the trajectory that you take and the origins, or essentially where you come from, particularly in your case, essentially because I'm familiar from the area where you're from, but maybe I should let you say, how did you grow up and how did that affect who you became?
Yeah, so a long story with a lot of turns, but let me try to make it short enough. I was born in Pontedera, which, apart from being the nice city and where the Piaggio group is, it's also the place where Scuola Superiore Sant'Anna is, or at least the lab of Bio-Rob, Scuola Superiore Sant'Anna is. And since I was a teenager, this had definitely an influence on me. I was visiting the lab during the open days and seeing the robots there, which was super cool. But if I have to be completely true to history with the small h, I wasn't struck by saying, oh, this is what I want to do. Actually, what I wanted to do is to be a musician. And so I decided I will do computer engineering to become a sound engineer, actually. And then I discovered during my first year that I liked math more. And then this pushed me towards, thinking, okay, should I move to a math degree or keep doing computer engineering? I decided to stay in computer engineering, but then I discovered that control theory was a nice thing in between that I could do. So I moved to control theory master. And then while doing control theory master, I discovered that I liked nonlinear control more than other kind of control. And the only group that was doing some kind of nonlinear control was the group of Antonio Bicchi, who is a roboticist. And so that's why I went into robotics in the end.
Amazing. I should mention for the listeners, those who are not familiar with Pontedera, that it's actually home to Piaggio, as you mentioned, and for Vespa lovers, it's a kind of an institution. I remember there's a museum of Piaggio there. So you start your career with Antonio Bicchi. He's world famous for, I would say, robotic manipulation, variable impedance actuators, haptics. And what was the topic of your PhD?
Yeah, I did my master thesis and also my PhD with Antonio, and we spanned several topics during my PhD, but probably the one where I spent most time were indeed robotic hands. At the time, and still today, but at the time Antonio was in all the group was pushing a lot towards this idea of building robotic hands that were mechanically intelligent. So they are able to solve part of the control problem or the manipulation problem directly at the mechanical level. And this is ended up to be a good part of my PhD, was to thinking about how you design these hands and then how do you control them or how you work with them to perform grasping and manipulation. This is in a sense had a big impact then on the way in which I thought about robotics in general, because the approach there was very much looking at a design problem, mechanical design problem, from the lenses of control engineering. We were trying to solve a control problem in the end. I mean, we don't do any explicit feedback loop or whatever, but we were all speaking that language. And that kind of started to put me from the perspective that there is control going on and there are control problems somehow connected to the actual physics of mechanical systems.
It's certainly what I liked. So obviously, while browsing the literature that you produced and your website on the internet, what I really liked about the description of your group is that you speak many languages, but not just human languages, but also mechanical design, machine learning, material science. But the lingua franca is nonlinear control, nonlinear dynamics, and control theory, which I obviously am a fan. So out of your PhD, there's so many publications that I don't think we have enough time to actually discuss all of them. I guess some representative ones are certainly the publication related to the PISA robotic hand that basically presents this new design that, as far as I understand, uses less actuators than previously done. I'm not an expert on robotic manipulation, although I find it extremely fascinating. So I would be curious if you could spend some words on the subject and what were the main innovations and where do we stand today also.
Yeah. So the publication that you are referring to is probably this SoftN 2 paper on TRO. And as the name suggests, SoftN 2 is this was a line of research that started before my PhD, not long before, but a few years before with the first ERC advanced grant of Antonio. And so the ideas come from there, but then we were pushing them further and further during the time I was there. And in that paper, we were really looking not just at grasping, so the capability of a robotic hand to take an object and basically keep it in the hand, and then if you move the arm, the object moves with you, but also the extremely more complex task of then reorienting the object by moving the fingers, which you can refer as in-hand manipulation. And the ideas, the combination of ideas that are there are, first of all, the fact that up to that point or up to a few years before, people, especially, Antonio was one, as you mentioned before, one of the pioneers of this research in the classic grasping and manipulation theories. People were really focusing on the object and completely neglecting the hand. So what you were trying to do is that you were trying to model, the object as for example, as a rigid body. You had a bunch of forces applied to this object, and you were just considering the hand as some kind of pure generator of forces and torques applied on the object. This allowed to really push research forward in many ways, but at some point we hit a hard constraint or hard limit, because this is not the reality of things. First of all, robotic hands cannot generate in such a transparent way force and torques. But also, this is not how human hands works, or in general an animal paw would work. So we started looking at nature, so how things happen in nature, and then we tried to extract these ideas and distill them and bring them to robotics. So how do this class of hands works? Basically, you have a bunch of degrees of freedom, so the hand can move for that specific hand in 19 ways, 19 different directions, so 19 degrees of freedom, but we have only 2 motors. And then the art stays into deciding what kind of movements this motor will generate, and then in which way the hand will react to interaction with the object and to the environment. Then when you look at things from this perspective, what you have is that the mechanics itself of the hand, so the springs and the dampers, because, this I did not mention, this hand is then generated by combining rigid components with elastic components and tendons and whatsoever. All these mechanical components ends up, when you write the equation, to produce a behavior which is kind of an equivalent of a local PD. So with the proportional terms implemented by the elasticity and the derivative by the dissipation. And this ends up working extremely better because then what you have is that, first of all, you don't know expensive sensors and motors to close the loop. You have the loop directly closed from the mechanical level. And second, by leaving out this, like the hands leaving the freedom to move basically in 17 direction because you are blocking only 2 with the motors, you are allowing the hand to adapt to the object. And this way you are letting the object guide the shape of the hand and the equilibrium of the forces rather than the other way around.
Fantastic. Yeah, it was fantastic to follow your line of thought. Just a clarification for the audience. I guess you were referring to dissipation. Dissipation is the derivative term and the elastic forces are the proportional term. Yeah, so I'm completely fascinated by this topic of embodying the intelligence in the mechanical design. I'm sure that this is going to be a leitmotif of this whole conversation. I think it's one of the frontiers of certainly nonlinear control, but probably also of robotics or soft robotics in a certain sense. Is that actually where your interest in softness or the fact that you can deform somehow an object and also embody the intelligence arose, or was it at some other point?
No, this arose from, the interest onto elasticity and deformability, yes, it came from there. But then the moving towards more control of soft robots came more for chance of how things then connect. Because there is an extra step in the story that I have not mentioned before, which is when I finished my master, then which was already on the robotic hands, then I said to Antonio, I liked very much this thing about robotic hands, it's very cool, but what I really like is nonlinear control. And he told me, if you want to do nonlinear control, then, at the time in the lab, people were very focused on these design aspects. And he told me, we used to do this before in the past, maybe we'll do it again in the future. But the place in Italy where you should go to do control of robot is, maybe I shouldn't say the exact place because then other people will, but he told me another university, let's put it like that. And then I said, I ended up waiting 1 year to start my PhD because I wanted to think about this. And then in the end, I said, okay, I like it here, so I will do the PhD on this stuff. But still, I really wanted to do more not classic control, but more control as classically intended. And then at some point, I had the opportunity to go to do a period abroad. And I went first to DLR and then to MIT. First to work with Daniel Bouchef for a very small period, and then to work with Daniela Russa. And it's in these two cases, but especially with Daniela for what concerned the soft robotics case, where I really had the opportunity to move and push more on the control of soft robot side, of continuum soft robot side. Because then when I got there, the initial discussion with Daniela were kind of along the line. So now we have these super cool systems. They kind of work. We can actuate them and they will move. And a continuum soft robots are, for people that are not aware about this, are systems that are inspired by octopuses or squids or elephant trunks. So systems that are made of continuously deformable materials.
We'll definitely clarify the definition later. I'll steer you in that direction.
Okay.
But you were saying about the discussions with Daniela?
Yeah, so Daniela was saying, okay, we have these amazing systems and they move and they do stuff, but we don't know how to control them. And you like control and can you do something? Can you design some controller for this? And I was like, hey, this is what I was waiting for.
It was your playground.
Yes. And then we started very much there to push forward with, then start a collaboration with Daniela, Antonio, and then also Robert Kachman from ETH was there. And Robert was doing a PhD with Daniela and was one of the main responsible of the development of those cool soft robots that Daniela was referring to. So we started Robert and I, to closely work together, me more on the control side and him more on the mechanical design side. And it was, very, very fun time.
Fantastic. I have way too many questions, and as I said, there's way too many publications that I would like to touch on. Maybe we can actually start from a publication that resulted from this collaboration. I had noted down in my notes, model-based dynamic feedback control of a planar soft robot. I hope that's representative. It's a paper where you develop a closed-loop dynamic controller for a continuous soft robot. Since we're starting, and as we mentioned them also previously, to mention what are soft robots, maybe it's a good time, a good stage to actually define them. I noted down that you also had contributed to the definition of soft robot in the Encyclopedia of Robotics. There will be obviously a link in the description. So maybe this is a good moment to say, what is a soft robot?
That's a very hard question to answer, but I can tell you how I define soft robots in that entry of the encyclopedia, which is something along the lines robotic system where you have elastic effects or elastic components that are not parasitic. So when you say elastic, you can largely use it as a synonym to softness. So you have some components that deform and can store elastic energy. And why the necessity to stress that are not parasitic? Because actually a huge amount of literature in control of robots and mechanical systems, starting from, I believe, the 80s or even earlier, maybe, and down to today, focuses on flexible joints, flexible links, flexible base, and you name it. So, and these are all mechanical systems where elasticity appears for parasitic reason. For example, in flexible link robots, you want to build a very lightweight robot, and then you end up having that your links are deform a little bit when you move. But this is something that you would prefer not to have. And then you have to design a controller that's basically trying to cancel these effects. While in soft robots, you really want the deformation to happen. And then one reason for you wanting it to happen is the example of the hand that I've given before. So to inject some kind of intelligence directly into the mechanics, for example. But there is also a matter of safety. So the fact that if you do that, then, or in the right way, then you can build the inherently safe mechanical system, safe robots. Yeah, and then you generate this system, which are called soft robots, and you can classify them in two groups. Articulated soft robots are the ones that from outside look more like a traditional robot. So they are they have a rigid skeleton, but they have more elasticity at the actuation level, a bit more like humans. We have a rigid skeleton, but then you have all our muscles and tendons are soft. And then you have continuum soft robots, and nowadays are also just called soft robots without the continuum, which are the ones that are in a sense more extreme, and they are made of continuously deformable material, like silicon rubbers, for example. And you can imagine them as a kind of something that tries to resemble the arm of an octopus.
That's fantastic. Actually, so in preparing this episode, I was remembering myself. So I studied nonlinear control as well in my PhD. And I remember that one classic example that was present in Isidori's book, one of the famous textbooks on nonlinear control, was precisely that of a robot with a flexible link, or maybe it was flexible joints. And so then in discussing also with other guests on the show, I realized that this is actually a relatively old topic in the sense that it's been studied also since quite a long time, right? And so I was trying to understand, where do we draw the boundary between, let's say, the study of softness and of robots with soft robotics? This would be my first question. And I guess the other point I wanted to make is that, maybe for context also for the audience, is that I guess in the past, the types of manipulators that we were building were, at least those that I imagine in my brain, are those that are actually assembling maybe a car. So the fact that you need extreme precision is something that you actually want to enforce at the cost of eliminating all these elasticities as we were discussing.
Yeah, exactly. So let me start from the first one, and probably I will also give contextually an answer to the second. Indeed, this is an extremely interesting point, because in this soft robotic classification I gave before, there is a difference in terms of like a biological inspiration, if you want, but there is also a strong difference or distinction in terms of communities. you have the people working on articulated soft robots that come indeed from all those people that, or kind of the, all those people that were working on flexibility. So you have more control people, or at least people that were more used to control theory and more used to work with more traditional robots in a sense. And then you have from the side, instead of continuums of robotics, these are all a lot of other communities, material scientists, biologists, you name it. They're the push for more trying to revolutionize the very idea of a robot. But then in the end, both of them started to call themselves soft robotics. And I think both of them were right in a sense, because then when you write down the equation, the two are remarkably similar. They have differences, but the two are remarkably similar. So indeed, at least from a dynamics and control point of view, it makes very much sense to put them together. Now, where do we draw the boundary? It's a tough question, because in my opinion, the boundary has to be drawn on the goal, on the control goal. So, okay, one first way to draw the boundary is on the level of, on the stiffness that your mechanism has. And then if the system is very soft, then you can call it soft robot. If it has elasticity but it's very stiff, then you don't call it soft robot. But I don't think that's the right way to do it. I mean, you can do this way, but I don't think that's the right way to do it. I prefer to say that this, instead to stress this parasitic difference, because in terms of control objective, then you get different goals. So if you have a parasitic spring, so you have this example you were mentioning from Isidori, where you have a motor, then a spring, and then your joint, then that spring is some kind of transmission mechanism that is not like quote unquote working properly, and then you don't want the spring, and then you want to use some, I don't know, feedback linearization to stay in the Isidori realms to kill the nonlinearity, and then cancel it out and make it behave as if the spring was not there. If instead it was yourself or some kind of other mechanical designer that put the spring there because you want some physical softness, then you have to start to rethink what is your control goal. And this is still an open question, an open challenge to try to define properly what you want to do with this soft robot. Because as control engineers, the more natural thing that you want to do is regulation of tracking, which translates into being precise. And in broadly, then we can discuss, but the vanilla way to do that is just to say, I have my joints, I want to regulate them, and I want to regulate more precisely as possible, and blah, blah. And this will end up making, in a way or another, making your mechanism stiff again. So canceling out the spring that you have put back in.
Mm-hmm. And in a way, you would defeat the purpose of actually leveraging a soft robot. And I guess we would have to talk about what is an equilibrium for a soft robot. But maybe this is actually a good stage to, well, move ahead both, let's say, chronologically in time. You are now at MIT and working with Daniela Russo. Of course, I could mention a bunch of applications. What I got out of, doing my own homework and reading the papers was that you work on a bunch of different models for these kind of systems, because we are talking about infinite dimensional systems. And I think a beautiful picture that you paint is precisely that of the Control Systems magazine paper. It's titled Model-Based Control of Soft Robots, a survey of the state of the art and open challenges. A real gem for the audience who have not read it yet. It's really a must, in my opinion. And there you beautifully explain all the different aspects that make soft robots and the control of soft robots special in many ways, going from models to discretizations, which seem to be a very important thing to talk about, model order reduction, simulation, and then actually what do we mean by, as we mentioned, regulation, control, etc. So maybe we can, I know it's impossible to squeeze in all the material that you nicely elaborated in that publication, but it would be amazing to talk about all of these aspects if possible.
Yes, for sure. And thanks again for the kind words. That writing that paper really came from, the excuse was an invitation from Helmut Hauser to do that. And if you end up looking at that paper, please also look at the other 3 papers in the same issues. They're all about soft robotics, and Helmut was the person in charge to coordinate this whole effort. But I was actually already working on it when he invited me to write it, because it was answering to a need that I had to start putting things, at least for me and then for students and then maybe for other people, to put things a bit more clear on paper, at least what in my mind was to be intended as control of these systems. So from now on, then we are talking explicitly about continuous soft robots. And for this system, is in a sense less tricky to define what you want to do, because since these are anyway not precise by default, and you don't have, you can argue that you don't have ways actually to cancel out all dynamics, then it's also fine to just try, at least at the beginning, to just make them as precise as possible or as stiff as possible. And this is what the literature there has been trying to do. And the reason why I find continuous soft robots so exciting is because they open up so many control challenges, and you have really the feeling to I imagine that people had back in the 80s when we were trying to figure out ways to control classic robots, or even classic robots before, of course, but more the first kind of underactuated robots, like a series elastic actuated robot and so on and so forth. So what does it mean to control a soft robot? As you mentioned, these are theoretical infinite dimensional systems, highly nonlinear. They are physical systems, meaning that you can describe them using Lagrangian or Hamiltonian formalism, if you wish. And the first thing you would think about, at least as a control theorist, would be these are infinite dimensional systems, so let's try to attack them with infinite dimensional control theory. Unfortunately, this is extremely hard, considering how complex is the dynamics and how complex is also the field of infinite dimensional control. So I believe that that's one way to go for the future, but for now, the largest part of the literature focus on first coming up with an intelligent discretization of the dynamics into a finite dimensional model, and then coming up with ways, with controllers to close the loop in this finite dimensional domain. And then the most sophisticated of these models these controllers are set up in such a way you can prove the convergence for any level of discretization, which is not the same, of course, as proving that the infinite dimensional system will converge, but it's a kind of weak convergence proof for the general case, because you can prove for a discretization which is as fine as you wish.
One comment that I would have at this point is, okay, maybe for the audience who haven't listened to other episodes, like the one with Miroslav Krstić, where we talked about, or Bassam Bamir, where we talked about partial differential equations, when we talk about infinite dimensional systems, there's basically a couple of reasons why that's the case. Either we have delays, or the system is actually spatially distributed, as is the case for most soft robots. So typically we have maybe, let's imagine an octopus arm. So what we are trying to control is not really the angle of a rigid link, but the actual tentacle, the whole tentacle. And as you were mentioning, controlling the system, well, requires, if we are going for a model-based solution, requires dealing with very complicated partial differential equations, typically nonlinear. Typically, you would have to specify also some proper boundary conditions. And I guess even in proving existence of solutions of those equations, which I guess in the physical world, we know that they exist, but in the theoretical world, these are quite ugly beasts to tame. And therefore, we introduce these sort of discretizations that replace those models. One nice talk that I've seen online in preparing for this episode is that you were somehow conceptualizing, this discretization as acting as basically leaving out some possibly unstable zeros for those who have some sort of frequency domain interpretation, some zero dynamics that we cannot really actuate. And in fact, these systems are very much underactuated. What does that mean actually in practice and also for control?
Yeah, so I think in order to answer this question, I have to briefly mention how you discretize this system. And when you look at them, if you want to model them precisely, these are PDEs. And for example, you can start by assuming that this is actually a slender soft robot, so it kind of look like a tentacle indeed. And if you do that, then you can already simplify your life and use a PDE which has just one special dimension. And you can use rod theories, like, for example, Cosimo rod theory, which are very well understood in continuum mechanics. So this is already a good starting point, and you inherit all these kind of existent proofs that you are mentioning from continuum mechanics. Now you have this system now, which is infinite dimension. You have this configuration space, which is the strain function. And the strain function tells you the infinitesimal deformation of this body at any point along its backbone. So you look at it as a rod, and then at that point you can tell infinitesimally how much it deforms, and that's the configuration of the robot. When you end up discretizing this, you can do it in several ways. The most commonly used one is called piecewise constant curvature or piecewise constant strain, where you are basically assuming that in space you define a bunch of nodes along your rod, and you say, okay, my strain, so this thing that describes how locally this thing deforms, is actually constant from node to node, constant in space, not in time. And this means if you look thinking about a planar robot, which only has curvature, so one of the 6 strains, this means that you are assuming that from node to node, the soft robot will always look like an arc of a circle. And if you do that, then you can associate to the weight of this constant term. It is going to be your configuration variable. And then, whatever. If you discretize in a segment, you are going to have n configuration variable. Each one of them, if you use a PCC model, piecewise constant curvature model, each one of them is going to represent the curvature of this arc. Okay, this is all nice because in theory then you can discretize to infinite. You can put the discretization order to infinite and recover your exact cluster rod, and you are happy about it. But then you realize that the number of your actuators, so the way in which you can actually have to influence the formation of this body, are finite. So they're not going to depend on the number of your discretization order. So if the discretization order is m and potentially goes to infinity, the number of actuators is m and it's going to be constant. This means that you have 2 choices as a designer, as a control engineer. Or either you trick yourself in believing that the system is fully actuated, meaning that you decide that you are going to select a discretization order which is equal to n equal to m. So you have as many domain of discretization as actuators. And this is what we did in that paper that we were citing as before. So this is a trick that it's kind of important because it creates a first bridge from control of classic mechanical system, rigid robots, fully actuated, to the domain of soft robots. And this is actually a trick that more or less explicitly a huge portion of the literature on soft robot control uses. So maybe you don't read it explicitly into the paper, but they start from an equation. And I think if you want to start to work on control soft robots, when you read a new paper, the first thing that you should check is if the authors are assuming that they have the same amount of degrees of freedom and degrees of actuators. Because this creates a huge difference. If this is the case, then you can basically borrow all things from the literature on robot control, on fully actuated mechanical system control. There's still a lot of interesting things to do in that space, especially from an experimental point of view. But from a theoretical point of view, it's, I believe, at least nowadays, it may be a bit less interesting. Instead, when the fun starts from a theoretical perspective, at least, is when you look at the system in a bit more realistic way and you say, okay, I actually have n degrees of freedom where n is bigger than m, And the difference between n and m, so n minus m, is going to be the dimension of your zero dynamics. So you're going to have, of course, twice, because you have also the velocities, but this means that you can, for example, perform a collocated control and block your actuators. So using a collocated feedback linearization, block your actuators, and still you will have all kind of deformation modes that are still active and can potentially become unstable. So if we now try to bring it really on the mechanical perspective, what these modes means is that assume you have your soft tentacle. The tentacle has a bunch of tendons that goes inside the body, and pulling these tendons, you can deform the body. And these tendons are connected to motors. Let's now imagine that you are gluing your motors, so there are like no way to move. And this is equivalent to have a collocated feedback linearization. So you're basically forcing your tendons not to change in length in any way. Now you can physically grasp your tentacle and start deforming it. And any deformation that you observe are actually deformations that are happening in the zero dynamics, because you have blocked your actuators, so the coordinate actuation direction are blocked, and the additional deformation that you are observing are the one happening in the underactuated directions.
I love this mental picture. It's amazing. Just wanted to chime in for a couple of clarifications for the audience, just because we are throwing so many technical terms that obviously I'm a control geek, so it's the fun part for me. But since we have a very diverse audience, I think it's important to clarify. First of all, I know that this is seemingly simple, but when you talk about configuration variables, I think we should imagine them as state variables for those who are not familiar with the robotics or Lagrangian systems terms. When we talk about zero dynamics, this is a concept that I believe has been introduced by Alberto Isidori as a nonlinear generalization of the concept of zero of a transfer function. And when you were saying that that goes unstable, well, we know that at least if we think about a frequency domain analogy, unstable zeros can create problems. And much in the same way, unstable zero dynamics can create problems or actually be exploited, I guess, as is the case of soft robots. I guess one point we didn't talk about concerning, let's say, the so many challenges that you were listing in that paper was the problem of regulation. Mm-hmm. What do we mean by also shape regulation at this point? Because that's actually what we are regulating. How do we choose equilibria, etc.? Yep. I'm quite fascinated by those questions, so I wonder whether you can elaborate on that.
Yeah, so we actually also on that point progressed further in these days. We now discovered, the proof is very simple, but with these things is really quite often the matter of formulating the question in the right way, and then the solution ends up not being too sophisticated once you've found the right question. So we discovered that the set of equilibria actually generate a manifold which is m-dimensional. So if you have m-independent actuators, you under a very mild condition, your set of configurations, so of steady state configuration that you can reach, it's going to be represented by an m-dimensional surface embedded in your configuration space. So when we talk about regulation for this robot, what we mean is that, first of all, we have to assume that our reference point has been drawn from this manifold. Otherwise, this cannot just be obtained. There are some interesting points to explore there, and as far as I know, they are unexplored in terms of studying what happens when you actually try to regulate something which is not on that manifold. But in general, it's convenient to start to assumption that the equilibrium is attainable, meaning that you can have a bunch of inputs that make that configuration an equilibrium. And then once you start from that assumption, you can think about how you close a loop such that the whole space, the whole m-dimensional space converges to that point. Yeah, and this is tricky, again, as you were very nicely explained before, because on m, quote-unquote, direction, you have control through your actuators, but then you have this kind of zeros, in a sense, nonlinear zeros, that can pull you in all kinds of directions and can also end up destabilizing your closed loop.
That's fantastic. And the way I imagine, for example, the problem of regulation in, say, a tentacle of an octopus is maybe like wiggling the tentacle around maybe some kind of object. And I don't know, I'm curious about what's the state of the art today. Like, what can we do and what is difficult to do in that sense?
So we have to distinguish state of the art in terms of our theoretical understanding of this and the state of the art what we can do in practice. In terms of theoretical understanding, we have now a clear picture on the structure of these equations, the way in which they, in the end, generalize the equations of unarticulated soft robots in a more challenging setting. More challenging because you have this theoretical infinite amount of degrees of freedom. So a lot of, let's say, zeros, or in another sense, a lot of very big passive, like zero dynamics. But also you have these inertia couplings and gravitational couplings that make the whole control more complex. So from the system point of view, you have a more clear understanding. And from a control point of view, what is called collocated control, it's a collocated shape control, I think is now a quite mature, or starts to be a quite mature niche. So we are now have more clear what kind of shapes you can stabilize and for which kind of soft robots by means of collocated control. And with collocated control, we mean using as control target or control output the configuration of the actuators. So what you do is that you want to control the whole shape, but instead of trying to control the whole shape, because it's too high dimensional, you select a fine amount of outputs, and as output, you just select the variables of your actuator, for example, the length of the tendons. This is a trick that comes from broadly underactuated mechanical system control, and that we bring to soft robotics. And there you have all kind of conditions that in terms of when you can do it and when you cannot do it, that are directly related on the way in which gravity, especially gravity or more in general external forces, act in this underactuated direction. And so it ends up to being a balance between how much elasticity you have in those directions, how much the elastic potential is acting in those directions, and how much instead gravity is having a destabilizing effect. Mm-hmm. So this from a theoretical perspective, our understanding right now. From a practical perspective, in a sense, we are in some ways beyond. So we are already able to do some things to move these soft robots around and do some kind of even tasks with them. In other ways, we are quite behind because, let me try to clarify why. Because in the cases which we are beyond, so which you can already show some nice video when this robot do things, you are in one of two conditions. Either you are just seeing a carefully engineered video for just the purpose of showcasing the hardware, and then the mechanical engineer or the control person spent some time to just play with the input so that it looks nice. So the hardware works, but it's not autonomous, it's not based on control. Or vice versa, the hardware has been designed, so the robot has been designed so that it's easy to control. So it's maybe stiff, or it's maybe not interacting much with the environment, so it's not exciting those unstable zeros that you were mentioning before, these zero dynamics. So you can kind of put yourself in a condition, either focusing on easy soft robots or easy situations, where even simpler controllers work, even if you don't have a full understanding of why they are working, not because you in a general control person are not intelligent enough, but more you in terms of our community still doesn't have an understanding of why these controllers are working. But you can kind of put a PID there, as you can imagine, and trying to play it around. And then you can get decent results. So I think the frontier now is to put these two things together, really have software robots that can finally go and generate complex and larger interaction with the environment in a controlled way, and that are also very soft, and so you don't need to stiffen them up so you are able to control them. You really want them to be like a tentacle of an octopus, and you want it to interact with the environment like a tentacle of an octopus. And for that, you really need this level of understanding of the dynamics that it's coming together only now.
Fantastic. I have a lot of comments concerning everything you just mentioned. First of all, well, one is actually the purpose, in a sense. So why do we actually care about controlling soft robots? We probably forgot it. We've been talking for almost an hour and we didn't even mention the pros and cons of these systems. We mentioned the difficulties from a control perspective, but I guess one of the clear pros is the fact that they are compliant by default. So certainly something that I want to touch on. Another thing you mentioned from the theoretical perspective was, you were mentioning how much elasticity. And it seems like the level of elasticity that one has in a certain mechanism also somehow plays the role of a parameter. And I always have in mind this picture. I don't know if it's more vivid now because of the victories of Yannick Sinner in tennis, but when a tennis player hits the ball, it's as if he's exploiting this elasticity we're making the arm progressively more rigid when we actually need it. But otherwise we do use elasticity at different times for coordination. So certainly that seems to be an interesting way forward for the control of soft or articulated soft robots too. And finally, I wanted third comment, to mention a quote from this paper that we've been discussing for quite some time. But in the introduction, you say, historically, across many application domains, model-based techniques are the first advanced control algorithms to appear and substitute heuristic rules. Data-driven and machine learning approaches usually come later when moving to more extreme control scenarios. This has been the case for standard robotics, but for soft robotics, somehow we've gone the other way around. So I don't want to necessarily jump into the whole machine learning versus traditional control quest just now, but I'm curious whether you have any thoughts about these comments.
Yeah, let's start from I believe the first one. So what are indeed the benefits or the reason why you may want to add elasticity or softness in your robots? And I feel that these are mostly well studied nowadays, at least from our perspective, from the control perspective, in the articulated soft robot community. But most of these considerations move or can be directly translated to continuous soft robots. But if you're interested, listener interested in understanding more from first principle what these are, I would suggest to go to that literature, because they had more chance and more time to look into this. And indeed, the example that you are giving about a tennis player is indeed an example which is very connected to articulated soft robots. So what you want to try to have an articulated soft robot is exactly like a human that plays tennis. So what are the advantages, so the reason why you may want to put elasticity there? The first one is safety. So if you study what happens when a multi-body system hits another one, which, for example, is a robot hitting a human, you can nicely show that if you want to minimize the energy transfer from one to the other, and so as a consequence make them more safe, you can first of all make them more lightweight. That's one thing you can do. And the other is to make them soft, so to add elastic elements that are decoupling your rigid bodies. And in this way, basically, each rigid body has to transfer its energy through the elastic components rather than directly through the various bodies. And then you can show that this will, in some cases, dramatically reduce energy transfer and thus damage to humans. So this is one reason, safety. And you can create clearly the mental picture of that by thinking about us humans when we are interacting with a fragile environment, how we are we are naturally compliant, or even, again, if we push towards the continuance of the case, like a tentacle, which is wrapping around an object in a way that you can imagine it's very safe. So if it will, like a tentacle, by itself, it will not hurt anyone. Of course, the complete animal can, but unless it stiffens. So this is the safety side. And then there is another one which I feel it's even more fascinating is the optimization side. So you make your dynamics complex in a sense by adding elastic elements, and in continuum soft robots also by adding extra degrees of freedom. And then these dynamics can generate open loop behaviors which are much more complex than the one that you will observe in a standard multibody system, rigid multibody system. And then you can start thinking, okay, how I can exploit these quote-unquote natural evolutions to perform tasks in a more intelligent way. And this is, again, something that comes from nature. So in biomechanics, it's well studied how animals, in order to run, they do it by stabilizing limit cycles that are already part of their dynamics. So you have these solutions, like periodic solutions in the multibody dynamics of your system. And then what the brain does is just stabilizing them rather than, as you do in a standard rigid robots, creating this thing by closed loop control. So I would say these are the two main reasons. There are many ways in which you can conceptualize these, but I think these are, in a nutshell, in a relatively big nutshell.
This is amazing. I was just thinking that every episode, unfortunately for me, feels like a race against time. I had the privilege to talk to you and many others for only a few hours. But you have to compress so much of information in just this very limited amount of time.
Yeah.
I was thinking about all the possible tangents that I would like to go now based on what you just said. So first of all, you're giving me a fantastic springboard for the next stage in your career. So when you went to Munich at DLR, we actually got stuck at MIT for quite some time. And we only talked about one single publication of resulting from that time. At least what I want to do is do justice to possibly one of the most interesting publications that I've read in a while. And it's a delightful conference paper that you wrote called The Soft Inverted Pendulum with Affine Curvature. When I read that paper, I said, this is something that is outstanding in the sense that I haven't read something like this for a while.
You're very kind.
I think kindness is due in this case. I just wanted to spend a few words on that and maybe actually move on to your next stage when you went to Munich, talking about Eigenmanifolds. This is something that I find super fascinating. I did work myself on some of those subjects at some point in my life. But yeah, maybe let's spend a few words on the soft inverted pendulum. To me, when I read that paper, that if I understood correctly, it introduces a template of an underactuated soft robot template in the. Here we're referring to, for those who don't know that specific paper, it's a paper written by Robert Fuhl and Daniel Kurtigich, Templates and Anchors. It's basically how to model, let's say, locomotion in animals. I wonder whether you had that in mind when you wrote this paper.
Actually, no.
Interesting.
So I know the paper, of course, that you mentioned, but this actually, that work ended up informing more my research on Eigenmanifolds that we can maybe discuss in a second. But indeed, I never thought about the connection, but the connection is also clearly there. So that's a very interesting point. I meant template as sometimes referred into the underactuated mechanical system literature as a sort of the simplest system that presents some kind of characteristics. And this was intended to be some sort of soft robotics equivalent of a cart pole system or a Furuso pendulum or whatever, Acrobot, you name it. So these are all 2 degrees of freedom systems, so systems that have a covariance space of dimension 2 and a state space of dimension 4, so position and velocities, and 1 degree of actuation, so 1 single actuator. And this system had a pivotal role in pushing forward the literature on control of underactuated system, because then you had really this very small or contained system in front of you. You could look at it, you can open, because usually in robotics, that's also something that maybe people, or in control of mechanical system, people that are not familiar with the field may not realize, but we end up not knowing what is inside our matrices, because we rely very much on properties of these various terms rather than what is inside those terms, because the actual expression becomes extremely complex, extremely long, and impossible to even inspect very quickly. And even, I mean, just to mention an example, if you try to create symbolically a software robot with 7 degrees of freedom, so relatively small software robot with PCC in the standard way, MATLAB, using symbolic toolbox in MATLAB, I know that MATLAB may not be the most sophisticated one, but it's quite powerful, right? It will block, and not because the symbolic derivation are too complex necessarily, but it will block even before when trying to open some of the files. So just parsing the scale of the model. So you have to come up with the alternative, so you can do that, blah, blah, blah. But whatever, I lost myself. What I wanted to say is that if instead you have a 2 degree of freedom system, you can still look at what inside these terms. And so you can maybe have a better feeling, a better understanding what was happening. And you can then, I mean, you have only 1 degree, actuated degree, only 1 zero in a sense, or 1-dimensional zero dynamics. And then you can start playing with all kind of control techniques to really have a fully clear understanding of that case, in the hope that then what you learn in this playground with this toy example, so actually toy example should have been the way in which maybe I should write the paper and call it toy example. It's a better name. So in which you can play with this toy example and then maybe learn something that you can then apply for more general cases.
It's fantastic. What I thought about in reading that paper, again, the soft inverted pendulum with affine curvature, there will be a link in the description, was that we did study, or at least many control theorists, and also beyond this, everybody who studied physics encounters the pendulum at some point. And somehow I never came across a soft pendulum, which is indeed something that we also encounter fairly frequently, but mathematically I never really studied that. And second, I also realized that maybe before I was referring to a paper that may not be, the audience may not be aware of, let's say, that by Robert Full and Daniel Kurtyshek, I hope I'm pronouncing it correctly. It's called Templates and Anchors, or at least that's the main title. Then it has also a subtitle. There will be a link in the description. There they introduced the spring-loaded inverted pendulum, essentially another template model, if you like, essentially as a way to represent jumping, hopping in legs, if you like, of animals in order to study locomotion. But I think actually we spent quite some time on, let's say, on the first part of your career. I really want to make sure that I touch on as many topics as I can in the limited time that we have available. So I think this is actually a good stage, because we mentioned it before, why to talk about eigenmanifolds, why these systems actually generate lots of very rich and interesting open loop dynamics. So maybe an intelligent way of controlling them would be to actually just make them land somehow on these dynamics. Well, I'll let you take it from here, maybe.
Yeah, so this system have, as I was saying before, quite interesting and more rich nonlinear dynamics. And then what people in the articulated software robotics community, maybe when was it, let's say 15 years ago, something like that, realized and started, maybe a bit less than 15 years, but let's say more or less those times, started to do was to say how we can exploit these more complex dynamics in a clean and a programmed way, an explicit way. And this was done in by using optimal control with analytical solution, and then also with numerical solutions. So this is one way to go, and there are some works that, for example, show the optimal pattern of both stiffness and actuation that you have to generate. For example, if you want to hammer something, which directly connects with what you were mentioning about Sinner before, about playing tennis. So you can clearly see in a reduced, like in a very simplified system already, with just one joint, with variable stiffness and just one link. If you want to maximize the energy, in this case, instead of minimizing for safety, you want to maximize it, for example, to hit the ball as strong as possible. There is actually a very elegant closed form solution on how you should
hit the ball,
basically. And you can compare it, there's this solution, to the equivalent that a rigid robot will have. And surprisingly, the soft robot can hit the ball much harder than a hard robot. Because you have this elastic element, you can store energy into the elastic element and then release the energy when you hit the ball. And then you can also think about similar things when you jump and these similar things. And the jumping is specifically something that we have been working a lot with my group in the past 2 or 3 years. So this is one way in which you can use optimality. In any way, you can exploit this embodied intelligence in soft robots. Another way is in periodic evolutions. And this now connects to research on eigenmanifolds, for example, that started from my postdoc at TUM and Della with Alin Al-Bushaffer. And there the idea is, again, comes from a long story or a long history of literature on this field, and also things Alin was been doing for several years, and comes from the realization that, let's again consider the simplest system that you can think about, like a point mass. So you have a point mass can only move in one direction, and assume you want this mass to move back and forth, like between 2 points forever. And you already know that this is the evolution that you want to have, because, I don't know, you can imagine some kind of pick and place task in an industrial setting, whatever, some kind of things you have already decided that this mass has to move back and forth at these 2 points. A classic control or robot control person, what will do is to say, okay, we can apply a force to this mass, and we can, I don't know, either use optimal control or a closed loop, do some trajectory tracking and move this mass back and forth between these 2 points by applying this force. But actually you have an alternative, and the alternative is to just take a spring, connect it to a wall, and connect it to this mass, and then have selected the spring with the right constant, such that naturally, in assumption of no dissipation, an ideal assumption of dissipation, naturally this mass will move as natural oscillation between these 2 points. So this is what happens with this very simplified system, but you can extend it and think about it in the context of a multi-body dynamic system, which is, for example, performing locomotion. You can see locomotion like a periodic movement, where each joint goes back and forth to configurations, but also in more general context, I mean, as in industrial operations, when you have to perform many times the same task. And if you take your multi-body dynamics, you add springs to it, or in general, some potential field to it, then you naturally see arising these families of, in this case, nonlinear oscillations that you have available as a control person. They are there in your system, so you can start thinking how I can excite them. So instead of forcing on your dynamics some kind of evolutions that you decided for some reason, that some trajectory that you decided for some reason you wanted to have, instead what you can do, you can look at your system, characterize the oscillatory behaviors that the system naturally would like to produce, and just help, in a sense, the system by means of closed loop control to express these oscillations by exciting them. And this is, within this line of research, is our works on eigenmanifolds and the corresponding control aspects connected to that. And eigenmanifolds, you can conceptualize them as a nonlinear extension of a linear eigenspace for multi-body dynamical systems. And for people that are instead more into nonlinear dynamics, these are essentially a subcase of Lyapunov subcenter manifolds.
It's amazing. First of all, one thing I want to mention to the audience is the fact that you have a very nice review paper there too, that is explaining, at least maybe it's a bit far back in time compared to where we stand now. So it's from 2020, a review of nonlinear modes in conservative mechanical systems. There you put up a very nice review of all the available notions of this concept of normal mode, eigenmanifolds, and all the related circle of ideas that essentially try to generalize this idea of eigenspace, eigenvalue of certain dynamical system. So certainly that's a starting point for our audience. There will be, again, a link in the description. But then again, what you started trying to do, because your purpose, or it's actually, well, I guess it's clear also based on the premise of this episode, is to somehow land or make through control your system efficiently land on those eigenmanifolds so that you exploit then the natural oscillations that the system can generate. So there's, again, a couple of papers that I have identified as interesting in this respect, but maybe you also have other ideas. And it's exciting efficient oscillations through eigenmanifold stabilization, as well as when do Lyapunov subcenter manifolds become eigenmanifolds. These are some that I have noted down. I wonder whether you can give us a brief overview at this point, just because I'm aware of time, but let's try to do justice to those two.
Yeah, so in the second is actually still under review. So it's a very recent one, and it's a work of Yannick Vogt, who is a PhD student in Twente, and it's a big collaboration with many people. And it's indeed about creating this connection with the more established theory of Lyapunov subcenter manifolds and these eigenmanifolds, trying to understand what are the kind of symmetries in your mechanical system that have to hold in order for the two being the same thing. This is, of course, extremely important from a theoretical perspective to have clear, you don't want to reinvent the wheel, so you want to connect with things that are already there, but also because then you can borrow all kinds of results from one field and throw them into the other. So this is what we do in that work, while in the other one, we propose indeed a relatively simple way to excite these oscillations by stabilizing these eigenmanifolds. So, and the eigenmanifold and the energy level of the orbit. So this is, it's a technique, it's a kind of a nonlinear PD plus an energy regulator that you can use to excite these orbits in a way that is not too model-based. In a sense, you use some information of the model, but you are not doing cancellations. And this is very important from instead a practical perspective or a control engineering perspective, because then when you go on the real system, we don't understand why, but we understand from a gut feeling, but not from a theoretical point of view. But when you do this kind of control and you try to exploit elasticity, you excite elasticity, you excite the natural evolutions via a controller which is not too model-based. So these two things adds up together into remarkably robust behavior. So you can end up perturbing your system in all kind of ways, blocking some joints, generating like putting your robot on an even terrain, because again, all these things then feed into the locomotion application mostly. So you can end up starting to model your robot as if it was standing on a flat ground, and then you put it on a ground which instead it's uneven, and this will still keep working. Because in a sense, what you're trying to do is just to regulate two intrinsic property of your system rather than forcing some evolution at the joint level. This is the kind of the gut feeling transferred through the lenses of control. And then you get this very nice and natural looking locomotion behavior that are very, very efficient, so order of magnitude more efficient than the gates that you will observe on a commercial legged robot or commercial quadruped. This took a long time, but we finally have a paper has been published like 2 weeks ago, I think, something like that, on IGRR from the first author is Davide Calzolari, who is now close to defend his PhD. and he's together with, of course, with Aline as well, Albuschaffer. And it's kind of a culmination of several years of research on this direction, where we finally demonstrate on quadruped, a fully elastic quadruped, complete pattern of locomotion on a real system and that walks or actually runs for 2 hours straight by excitation of this manifold. So it's a very nice result that Davide managed to obtain.
Extremely fascinating. It reminds me also of the passive walker. I forget the actual author of that.
There are, these passive walkers are kind of the main inspirations for all of this. I mean, we have here in Delft, actually, I have to mention him. The head of my department, Martijn Wisse, was one of the people at the time I was working on this, but there are a bunch of people were working on these robots, which are like the extreme version of what we're talking about. They were robots with no motors. So we're just like, you push them and then they start walk until the energy is dissipated. But then there was this kind of limit was hit by the fact that, okay, you were able to study them by using some nonlinear dynamics, but there was some difficulties to then bring them to the level of autonomy and then the level of multi-body joint complexity that you really need then to have a real robot. And this required some kind of change of perspective that happened over there. So that literature kind of died out. This passive walker literature died out, and then now it's not just from us, but from also other groups. It's kind of reinvigorated through a different perspective, but still having them as the kind of main source of inspiration.
Yeah, I mean, you're again serving me a wonderful assist to move forward to the concept of physical intelligence, physical control, embodied intelligence. One quick question on the Eigenmanifolds thread of research. Well, 2 questions, and then maybe we can move forward to your actual present job. Those questions are, well, first of all, where is it going? So where do you see that going? And it's probably in this direction of physical control. And the other one is technical. So when I did my self-study concepts like Eigenmanifolds, etc., one of the bottlenecks there was the fact that you always have to solve relatively ugly partial differential equations. So numerically, these concepts, while appealing theoretically, are difficult to actually compute and determine. So I'm curious, how do you tackle those challenges?
Yeah, so indeed, these are quite complex beasts. And the way in which we tackle them is, in a sense, with a dirty trick. And the dirty trick is that we start from the assumptions that we have a solution. Okay? And then you start from the assumption you have the solution, and you build up all your, say, control theory from there. So a solution for the PDE, basically. We then also exploit in some places the fact that that is a solution of the PDE, so the tangency constraints. But in the controller, this kind of nonlinear PDE, for example, you have the solution explicitly appearing. So you have explicit in a sense that when you have the solution, you plug it there, and then you can prove that it converges. So this is a dirty trick, but it allows at least to say something about the convergence and all. And then, in the sense, decouple it from the challenge of finding that solution. And then the way in which you can find it, there are multiple ways. The way in which we usually do it is either by Ritz-Galerking way. So these are things that other people came up with. So it's not our contribution. But basically, you assume that your solution of the PDE lives in some subspace, like polynomials of some order, and then you can transform the PDE in an algebraic equation that you can solve in closed form. Or we use, for more complex system, we use continuation methods. And for those, you can rely on the fact that you know from the theory that the eigenmanifold is tangent to the eigenspace of the linearized system at the equilibrium. So you have a direction which you can start shooting from, which is the direction of the eigenspace. And then from there you do continuation, and you kind of look for the point which you still have a closed orbit starting from there.
Fantastic. Again, I actually checked my phone as we were discussing, and there is not only a roboticist, but also artists themselves building these machines that actually passively walk. It's called strand-based.
He's from here, right?
Yeah, exactly. He should be Dutch, I guess. Theo Jansen or
Theo
something like this.
He's from Delft, so he works in Delft.
Oh, there you go. Okay.
So he's
what a nice coincidence.
Yes. I actually didn't know when I moved here, but yes. So, and he does this very cool thing. So just you should go online and check. In Netherlands, sometimes coming to Netherlands, he also does this. So he creates these super big creatures, mechanical creatures that walk using the wind and the natural dynamics. And they're called strand-based because I'm probably butchering the name in Dutch, but it means beast of the seaside. And he has these videos on the beach, and he does this demonstration that you can participate in, where he shows these robots, and it's very cool. So I went there. It was nice.
I also like the fact that here he is bridging robotics and arts as well. I really want to give the spotlight to now your own lab, so the present. If you like, we managed to get to the present in about more than 1 hour, and there's a lot to talk about. First of all, this concept of embodied intelligence, physical control. You have a very nice piece on, I believe, science robotics.
Yes.
And also a recent Nature paper also along, not necessarily identical ideas, but tangent ideas in many ways about synergistic control. So I wonder, how do we best give an overview now to the audience about what you're doing and where you're going?
So, in a sense, all the things that we discussed so far are continuing within my lab. And more in general, one at some point starts to think what are... I tend to go in many directions. And we also start to do research on fluids and on machine learning more and more, both not just on the application of methods, but also really on the methods themselves and how they connect to control theory, and so on and so forth. So in some sense, a bit of a limit of mine. I tend to go all over the place, and this is also reflected in my group, but it's also a lot of fun. But one thing that connects a lot of this research line is that initial idea that, or these initial concepts that I learned from my initial works on the robotic hands in Antonio's lab. So this idea that you can move some of the intelligence into the body, but not just that, it's a version of this idea from the lenses of someone that comes from control theory. The fact that there is some control loop that is going on into the body of the robot. Now, or in a sense, you can take part of this dynamics and connect it with a control loop, as in the excitation of the nonlinear oscillations case. So now what this means exactly, I don't know, because I think there is not a clear formalization or general formalization of this, but this is indeed the point of that we make into this paper about physical control that we were mentioning before. And it stems from, on one side, all these kind of ideas that are there in several works that I mentioned before. And these also come from all other kind of works more on continuums of the robotics, which are showcasing examples more and more often of mechanical systems that can produce intelligent motions without relying on an explicit controller. So, with explicit controller, I mean something which is implemented with sensors, actuators, and some microcontroller things you read. And the way in which I like to look at it is to go back to the classic example of when the people talk about the early days of feedback control. People like to show this example of the regulator of pressure in the steam engine that was implemented during the Industrial Revolution, that basically it's a mechanical system, a very
Maxwell's flywheel.
Yes, exactly.
We have, in the first episode of this podcast, actually, we do talk about that.
Fantastic. So this is a very common example, right? So basically it's a very simple mechanical trick to basically implement a proportional controller on the pressure of your steam in your machine. And then, every time that I heard about it as a student of control theory, or more control engineering in this case, I always interpret it as, okay, these were the early days, then we evolved, we made steps forward, now we have microcontrollers, and now we can not rely on this primitive way of implementing a controller. Now we can have sensors, we have actuators, we have microcontrollers, we can close the loop this way. But actually, I feel that for some things, it's now becoming more and more clear that this may not be the way in which you want to go. So we are very good in designing actuators, we are good in designing sensors, we are very good in designing microcontrollers. So this has worked very well. And it's worked well also for a situation which is, in my opinion, is suboptimal to do that. And just because we have been so good in developing this component and that we just use this toolbox, but this kind of, in my opinion, in the design space is a local minimum in many, many cases. What instead you should do is to start think on how you can bring back those early ideas, those early ways of implementing controllers, and you have many others. You have ways of implementing integrals with the water tanks, and so a lot of very interesting solutions. How you can bring them back in using new technologies, and how you can start conceptualizing some behaviors that we observe in soft robots or in other kind of mechanical system through these lenses, and then how you can then use eventually, I hope, control theory to design mechanical system.
Fantastic. You also mentioned en passant the water clocks of Ctesibius. Technically speaking, the clepsydras, they were, in Greek, that means stealing time, which is, I find, fantastic as a name. And I guess much of this line of research is condensed, as I mentioned, in this, or at least this vision is condensed in a few recent papers. One that struck my interest was this physical control, a new avenue to achieve intelligence in soft robotics. I particularly like a passage there where you say one fundamental limitation when you compare to how animals actually move and, perform tasks in dynamic and uncertain environments. You say one fundamental limitation is the reliance on digital computation, which is appropriate for high-level reasoning, but it's not the natural language of motion generation. So what is the way forward for you in order to go beyond digital computation?
The way beyond, the way forward is in find a way to bring together people that are in control and people that are in nonlinear dynamics and people that are in mechanics. In mechanics in the sense of theoretical mechanics, at least to understand how you can conceptualize and formalize this challenge, and then of course put all these people together with the mechanical engineers or the people that actually build the stuff, so that we don't end up thinking about things that cannot be actually realized. But in a sense, as I see this as a future, and we basically have zero results in this direction, so it's very much more like a belief than it's a scientific statement. I feel that assuming that something can be implemented by a body, a physical system, will end up imposing some kind of constraints on the structure of your controllers. And then it becomes a very interesting challenge to design this controller in such a way that can be physically implemented. And so this is, in my opinion, the way forward. And then soft robotics, and then the people that come more from materials and extreme mechanics and so on and so forth that are in soft robotics, in continuous soft robotics, are showing us that you can put in your robot all kind of cool stuff like pneumatics and materials that have their own dynamics. So you have really an alphabet of possible dynamics, which is very large and very complex, and it will be a challenge to understand how to put all this together, understand what are the right things to use. But I strongly believe that the soft robotics community will benefit from people that now can bring these ideas and give them control form. And if I can step back a little bit, so this concept of embodying intelligence is something that has been around for a while. And this control view to the embodying intelligence is just one of the possible views. For example, another one which is quite advanced, has been advanced quite a lot in the years. Like, for example, I mentioned before Helmut Hauser is one of the pioneers of this, is morphological computation, which is one way to formalize the idea that a physical body can perform computations. So it's another way to say, let's get rid of microcontrollers, let's get rid of digital components, but it's a different view to the point. It's more a view of how I can do computing. So more it's an information theory point of view rather than a control theory point of view. So this trend of saying, let's use the body, the physical body, to do stuff rather than looking it as part of the problem to solve, let's move it into the solution, is a trend that has been pushed originally by Rolf Pfeiffer and from a philosophical point of view, but then has all kind of extension or tangents in philosophy of mind and in engineering and so on and so forth.
The Playful Machine.
Yes.
It's one of the books that I have on my shelves here. Fantastic. As you mentioned also, the pointer to morphological computation. Also in the Control Systems magazine paper that we were referring before, there's also a piece written by Helmut Hauser together with collaborators as well. Extremely fascinating. And again, another item in the reading list, if you like, for our listeners. I'm aware of time, and so I would like to condense as much information as I can in this episode. There's essentially one hot take that I would like to get from you, and then since you also served me a nice assist towards leadership, in a sense, service towards the robotics and control community. I know that you've been a member of the technical committee on robot control. I know that it's been growing, so it would be nice to give it also some spotlight, if possible, through this podcast. And the question I had concerning everything you're doing in the lab, you're doing crazy cool things, from fully quadrupeds without brains, or I've seen works on prosthetics, again on feet that are more compliant. In all of this, I know that it sounds maybe a stupid and technical question, but I keep thinking about the identification question somehow, because these systems are terribly described in a certain sense, if I try to think about any possible parameterization that I can think of. So then learning comes into the picture, and then we start the usual fight between model-based control versus machine learning. And there seems to be certainly a trade-off. I know that you have also been working on physics-informed learning as well. I'm curious about your take on the role of learning in all of this, and maybe in particular in soft robotics.
So identification can be addressed using standard nonlinear identification methods in principle, and this is how we do it when we work in the context of purely model-based control techniques. This is quite a tough thing to do in practice, but we have not invented anything new as far as I know. There we are only using methods in the literature, but it's definitely not easy to do, and I agree with you. I actually like very much to think about how machine learning can help in robotics in general and soft robotics. So I have one hot take and then one more technical opinion. And then one hot take, my hot take is that people in academia shouldn't care about how to make things work, but why they work.
This is definitely a hot take.
Or at least some people in academia should exist that don't care about this. Maybe not all of them, but make it a warm take, not a hot take. I certainly tend to care a bit less about making things necessarily work. I mean, some part of my research is about that, and also we are now pushing for high-TRL application. We have this company and definitely something that I care about. But in a world, especially in robotics, where now we are more and more seeing companies that are pushing the boundary, one should ask themselves what is the role of academia. And in my feeling, the role of academia, academic research, is about understanding the functioning of things. Now, this can be the understanding of machine learning, because we have to understand it as well. So this is not a take against machine learning. And can also be the understanding of the nature of the control problem of a soft robot, for example. So one reason why you want to look into first principle control or model-based control, there are strong practical reason for why you want to do this, but there is also a more fundamental academic reason, which is, in my opinion, is studying the control of this system is, through first principle, is a way to really understand what are the more underlying property and structure of such a systems, beyond then how the final performance that you can get. Okay. So this was my kind of hot take. The more technical and practical and point of view, what is the role of the two, or first principle or model based? First principle, I believe first principle control or model-based control should be used in wherever is possible to use, because you just have more control on what is happening. You have interpretability, and you can kind of more easily figure out where things fail, why they are failing. In industry, they don't really care about our proofs, but it's also nice to have some proofs, because at least it gives you a sense of what you have to do in order to make things work, rather than trial and error. So these are all things, and these are, of course, proofs are things that more easily come, at least I believe today, with the current state of theories, more easily come when you work on first principle techniques. So these are all things that are in favor of first principle techniques. Things that are in favor of machine learning are, first of all, some things that are more on higher level, more on the cognitive level, are just so much easier to do with machine learning than with first principle model. And one that I'm thinking about, it's even like trivial, but it's what you do with imitation learning, which is or learning by demonstration, which is something that I end up working more and more in the past years, also thanks to collaboration with Jens Kober, who is in my same department. He's an expert on the field. In imitation learning, what you want to do is to show a task to a robot by, for example, physically moving the robot. And the robot should be able to generalize within a small context, a simple context, the execution of this task. And this is such a natural way of programming a robot, right? That it's just, to me, no question that you should do it this way, in a data-driven way, that you show the robot what to do, and then the robot should be able to understand that it has to move an object from that point to that point, and it's so natural, and do it with first principle is not even clear what it means to do it in first principle.
That would be a formidable task.
Yes.
To do it in a model-based fashion.
Yeah, but it's a very natural. It's a task that is very naturally formulated as a more in a data-driven, in a sense. It's more explicitly a regression problem, if you want. Okay, so this is one answer. Another answer is, in some cases, like, for example, when you use some form of reinforcement learning, for systems that are very hard to model or to attack with model-based techniques, like, for example, walking systems, or this nonlinear hybrid system, it came out that kind of reinforcement learning attack all systems in the same way. So the ones which are more easy to deal with first principle, you should deal with first principle, but the ones that are very tricky to attack with first principle, like these ones with a lot of discontinuity, hybrid behaviors, then using a method that works the same way for everything, it's kind of convenient. And then the third reason, that is the one that I'm most fascinated about, is indeed connecting now back to your initial question, which is how you do nonlinear identification with machine learning. And of course, there has been a lot of research in the control community. So I am a child here, in many things, but especially here with respect to things that have been done. But I'm just enjoying it. And I think it's very nice to think about how you can combine machine learning-based nonlinear identification with control. And I'm specifically interested, at least with my group, in looking at the case of physical systems. And as you mentioned, physics-informed learning. And there is a perspective to that, which is like, okay, if I want to learn the dynamic model, and then to use it for control, I may want to embed into the learning process some understanding of the physical rules that I already know they are underlying my data. So why, like some symmetries, conservation of energy, blah, blah, blah. Why do I need to learn from data? I know that all physical system having, so let's just embed them in the learning model. So I will need less data to train. I will have a more stable training. That's a motivation. But I think another very interesting motivation is the fact that these techniques can be used to learn models that have a mathematical structure, which is the one of a Lagrangian system, or even a Lagrangian system with some particular form. And then we connect back to what I was saying before. So in a control of mechanical system or physical system, quite often we don't look what is inside our matrices or our things. We are just happy that these matrices appear in a certain structure, a certain combination, and they have some property like positive definite, or they are a potential, or blah, blah, blah. And you can enforce this property in your learned model. And then you can just deploy these models into model-based controllers, which are not MPC, but they are like Lyapunov-based, for example. And the whole proof will just work. And then you can start thinking about using a robust nonlinear control to give some kind of characterization of how good has to be your learning process in order for this explicit closed loop to work. So I diverge once again, but these are some things that we are now working on and I think are very, very interesting. And they are very important for soft robots because, soft robots are just a very complex mechanical system. So it makes sense to use these techniques in general. So they're just a very nice test condition for these techniques, but also because soft robots inherently have a huge variability of dynamic behaviors from soft robot to soft robot. So same design, different behavior because the fabrication methods are inherently create this variability. They have variability in time because of the use, but also because they are temperature dependent, humidity dependent, you name it. But also they have variability in terms of their environment. So they are systems that are built to interact with the environment. And if you want to make them able to interact with any environment, you cannot assume that you have everything modeled and identified in advance. Because the dynamic of an unknown and unstructured environment, you have to somehow infer from your interaction with it.
Mm-hmm. Amen. I love, again, all the circle of ideas that you nicely lined up. I'll probably point the audience at this point to a paper that you recently published at NeurIPS on physics-informed neural networks that essentially incorporate this Lagrangian structure that provides simulation-accurate and control-ready models. But again, I'm aware of time and I really want to give you the spotlight to some of the activities that you're doing within the technical committee at IEEE RAS on robot control. You're really trying to bridge the two fields together with, of course, many others. And also to a recent entrepreneurial endeavor that you launched into. It's called Embodied AI. I know that you're a co-founder. And so I was just wondering, on both sides, what are you trying to do? What are the initiatives, for example, in the context of, let's say, this technical committee that we can expect? How do people engage with the robot control community? And on the entrepreneurial side, I guess what is interesting to me is what is the killer app or the killer example where soft robotics will really shine? And I'm curious whether you think that's agri-tech, so the next step in agriculture, whereby we're going to use robots rather than humans, or something else?
So let me start from the company. And there I am already contradicting myself, saying that I'm not interested in making things work and then doing a company, because in the end I'm also interested into that. I actually became more and more interested into seeing things moving outside of academia in more recent year. Before I was, especially when I was a student, I was very much more extreme in this idea that I don't really care about things working.
I think many of us start like that.
Yeah. So here, this company is called Embodied AI and is incorporated in Switzerland because it comes from a collaboration between Josie Hook's group at EPFL and my group, and starts from the works of many people on both sides. But if I will give one single name, is Francesco Stella, who graduated with us, co-supervised by us a few months ago, and now is CEO of the company. And this started with the idea of bringing soft manipulators to market. It is now evolving in its own direction. And we are figuring out what is the killer application, of course. But I believe that soft robots are the way to go to really bring robots in human spaces. And this boils down to this inherent safety that they have. There are a few other characteristics connected to the costs and the resilience, but the inherent safety is really the point, because you can be very forgiving with your autonomy and also be very forgiving of what the humans will do to the robot. And so this is where we want to target. And I believe that if we are going to see robots in a retail space, for example, in a supermarket, in the short term, my bet is this will be soft robots, because of this very natural and inherent safety aspect that they have, that really simplifies the whole deployment of the system. So this is the company, and the technical committee is actually a very new thing. So we started it a few months ago. And this is something I've been thinking about for a while, and then finally things came together not long ago, when I started to discuss first with Manuel Kepler, and then with Sylvia Herbert and Kaoru Yamamoto, and which are now the four of us are the four co-chair of this technical committee in IEEE Robotic Automation Society. And it comes from the general sense of all us people working on control, or at least partially working on control in the robotic domain, in kind of not being, seeing our field not being represented in a sense anymore. When you go to control conference, robotics is an application, which is also no more very fashionable. When you go to robotics conference, control is the thing that those weird people do, and anyway, wasn't it a problem solved? And while at the same time, there is a huge portion of the robotics society that is working on control, or trying to work on control. And this we have seen because we have created this technical committee, and then in, I think it's 6 months, something like that, we already have more than 500 people that register, and this is still growing. So this shows that the people are there, and there is actually the need for that. And what we want to do is to help to do some critical mass around this topic, and create better connection with the other societies. And this is something that we are starting to do now that the TC is better established, specifically with IFAC and with IEEE CSS. And then indeed create critical mass, and especially for the young people, because we have been seeing more and more that people that are interested in the control aspect of the problem quickly get this in a state in which you have all these students that like control. Some of them like control, they do their thesis, and then they start to maybe they get the chance to get to a conference and then they tell you, hey, but no one really cares about what I do. It's all about topic X and topic Y, and I will not mention these topics, but other things. There is nothing bad against all these other topics, and there is the standard waves of evolutions of, this is how academia works, right? There is some moment there is more interest in one thing and another moment in another, so this is perfectly fine. But there is this bag of human capital that we risk to lose, because then these people are leaving academia because they feel that is what they like is not really of interest, while it's not the case. And this bag of knowledge, because all these things that we now know about control of robots, if we don't have people that keep pushing them forward and bringing them to the next generation, they are going to disappear. So we want to do education, we want to do some critical mass, and we want to engage with people. So if you are interested, get in touch.
Yep. I guess one last question. The question is always the same. So any advice to future students?
So I think one single thing that I would say to myself if I were to go back in time is that to not being too fixated on finding your own direction necessarily. Many times what just happens is that you start to work on something, and if you are in a right environment with the right people, you will just grow passionate about it, and you will find your own unique ways to contribute to that field, even if it's not what in your mind was the field you were supposed to contribute. And in a few years, it will become the thing that you love. And this I've seen happening to many, many times. So it's good to have a direction in mind. I want to do this, I want to do that, but then think about the opportunity you have in front of you, the people, the nice people you can work with, and that's the most important thing. And then the fun, think about something that you have fun doing, and everything else will follow.
Science is, after all, a human endeavor.
Yep.
Well, Cosimo, it's been a real pleasure to have you on the show. Thank you so much for joining us.
Thank you. Thank you, Alberto.
Thank you for listening. I hope you liked the show today. If you enjoyed the podcast, please consider giving us 5 stars on Apple Podcasts, follow us on Spotify, support on Patreon or PayPal, and connect with us on social media platforms. See you next time.